Hi everyone, my name is Juan, and our goal for this problem in this hackathon is to maximize F1 score on the lone default dataset while ensuring our best performing classifier was well fitted, meaning it generalizes well without overfitting or underfitting. In this presentation, we'll discuss how we improved model performance, what we did to access and improve model fit, what didn't work and why, as well as what we would do with more time. The first part, improving classifier performance. For the model comparison, we evaluated logistic regression, decision tree, random forest, gradient boosting, XGBoost, as well as H2O AutoML. All models were then evaluated using stratified k-fold cross-validation with F1 score. F1 score was chosen because the dataset is imbalanced and both false positive and false negatives carry financial consequences. Our best performing model was a tree-based ensemble between XGBoost as well as GPM, which achieved the highest cross-validated F1 and best Kaggle leaderboard performance. In terms of feature engineering, including what didn't work for our model, we performed extensive feature engineering to test whether domain-inspired interactions would improve performance. We created 15 engineered features, including interaction and ratio features such as loan amount times interest rate, debt to income times rate, interest rate relative to credit score, income per age, income per employment year, loan to income alternative ratio, loan per credit history year, age minus credit history length, normalized credit score, a high debt to income flag, high rate flag, low credit score flag, previous default times high rate interaction, young and short credit history flag, as well as large loan flag. These engineered features, while did improve our F1 score, did not improve our Kaggle performance. The reason why they likely didn't add work or add on to performance was that they added noise. The tree-based ensemble models, such as GPM and XGBoost, automatically capture nonlinear relationships, as well as model feature interactions and perform internal feature selection. Many of our engineered features were redundant transformations of existing variables or are linear combinations of already informative features and binary thresholds flags that could also potentially lose on information. Instead of adding signal, they increased dimensionality, added correlated features, and introduced noise, which slightly increased variance without improving bias, leading to marginally worse validation F1 score and worse Kaggle performance. So then we made the deliberate decision to remove them, demonstrating a simpler model or model simplification for better generalization capabilities. In terms of handling class imbalance, we experimented with smooth, borderline smooth. However, both techniques did not seem to be the best. And that is because for our best model, which was a GBM or XGB tree-based ensemble model, they handle imbalance naturally via splitting criteria and can use the scale post weight or internal weighting and much more robust to skewed distributions. Our implication or our usage of smooth or borderline smooth introduced synthetic samples that blurred class boundaries, increased overlap between classes, and also added noise in high-dimensional feature space. This increased false positive and reduced precision, lowering our F1, ultimately allowing the tree-based model to handle imbalance internally perform the best. And this was validated through cross-validation comparisons. In terms of hyperparameter tuning, we improve model performance through stratified k-fold CV, threshold tuning, model-specific hyperparameter optimization, as well as H2O AutoML with a five-fold CV split. Comparing our untuned versus tuned models, we use validation F1, uh, and we want to see that variance decrease as well as leaderboard score on the Kaggle improve significantly. This would confirm that our improvements were due to better generalization, not overfitting. In terms of accessing and improving our model fit, our validation strategy was using a stratified k-fold cross-validation, learning curves, confusion matrix, precision recall curve, and threshold optimization. K-fold CV reduced variance from a single split and gave a more stable estimate of our generalization. For our learning curves on our first logistic model, our learning curves exhibit potential signs of underfitting, signaling that the logistic regression model might be too simple to model um, our data. We then moved on to the logistic regression with borderline smooth, and while the model did seem to improve on cross-validation F1, the model was still underfitting. Now, moving on to the decision tree learning curve, this model potentially is depicting that decision tree model is overfitting as the gap between the training F1 and the CV F1 is very large and does not seem to converge well, even when the number of training samples increases. Um, Moving on to the random forest. The random forest was quite similar to the decision tree, although the mean CV for F1 did improve, the gap between the training F1 and the CV F1 was still very large, and they did not converge, signifying that this model was overfitted. However, when we move on to our GBM model without smoothing, this model appears to be much more well fitted. Um, the training F1 and the CV F1 seem to converge and were much more narrower at larger number of training samples, and their F1 were much more equal. When we move on to our XG boost model, it did signal the same with our GBM model, in terms at that this model had a strong validation F1, no widening gap, and performance stabilized with more model. We can then conclude that our best performing model is well fitted, and it is either a combination of GPM or XGBoost. We then, after identifying our best model is a tree and sample based model, we run auto H2O ML to identify the best model was happened to be a GPM model. Then we move on to the confusion matrix and business implications. We analyze that for our confusion matrix, false negatives means missed defaults or potential financial loss, or uh, lending money to someone that will not be able to pay back the loan risk. False positives, however, in this times means that we rejected good borrowers, meaning a loss of potential revenue. Our model predicted um, and we then used our precision and recall curve to select the probability threshold that maximize our F1. In terms of threshold analytics, we did not deliberately rely on the default 0.5 thresholds. However, for our model, the threshold 0.3 would give us zero false positive and zero false negative, which would be the best threshold choice for our current model, because we do not incur any financial loss or also do not miss out on any good borrowers missing any potential revenue. This reflects real-world credit risk strategy where thresholds shift depending on macroeconomic conditions as well as risk tolerance. If we had more time, we would incorporate external data sets such as macroeconomic indicators, including unemployment rate and CPI, as well as regional economic conditions, as well as deeper credit bureau features of each individual lenders. Now, to move it into production, our production monitoring strategy and how we handle drift detection, which would be we would implement it, data drift protection, feature distribution monitoring, ongoing F1 tracking, periodically threshold recalculation, and finding the best threshold, scheduled retraining with new data coming in. And this would ensure that our sustained performance over time, as well as good generalization capabilities. To summarize, we compared multiple classifiers and selected the best performing ensemble model. We performed extensive feature engineering and correctly removed engineered features that added noise. We tested smooth, borderline smooth, but found tree-based models handled imbalance better without synthetic sampling. We use cross-validation, learning curves, precision and recall curves, as well as threshold tuning to ensure the model was well fitted, generalizes well, and fit with our business objective. And our final model demonstrates strong generalization with minimal overfitting. Thank you very much. That is all.